Hello students, today we are going to start another topic of our chapter Gravitation. The objective of today's topic is to study about gravitational field and gravitational potential, under which we are going to study about gravitational field, intensity of gravitational field, gravitational potential and gravitational potential energy. First of all, we will study about gravitational field. Students, it is space around a mass where gravitational force of attraction is felt. So, gravitational field is basically a space around the mass where you can experience the gravitational force of attraction. So, next we will study about intensity of gravitational field. Intensity of gravitational field or gravitational field strength at any point in a gravitational field is made by the force experienced by a unit mass placed at that point. We have already read about acceleration due to gravity. If you remember, acceleration due to gravity at equator is minimum, whereas it is maximum at poles. Due to this acceleration due to gravity, there is difference in the weight of a person at equator and at poles. Suppose a person has a mass of 100 kg, then its weight will be 978 Newton at equator and 983 Newton at poles. Reason being because W is equal to M means mass into G means acceleration due to gravity, and if G value changes, weight also changes, and weight is the force of attraction with which a body is attracted towards the center of the earth. It means that intensity of gravitational field is different at equator and poles, or you can say that strength of gravitational field is different at different points. So, at any point in a gravitational field, the force experienced per unit mass is called intensity of gravitational field. So, formula for intensity of gravitational field is force divided by mass, and we are going to denote intensity of gravitational field with capital E. So, force divided by mass is called intensity of gravitational field. Intensity of gravitational field E is a vector quantity, means it has both magnitude as well as direction. SI unit of E is Newton per kilogram. You can see here SI unit of force is Newton, so Newton, and for that, and divided by mass, its SI unit is kilogram. So SI unit of E is Newton per kilogram. Now dimensional formula. It is very important in physics. Whenever you are going to read about any kind of physical quantity, please keep this thing in your mind that you should know its dimensional formula too. So it is mLt minus 2 multiplied by m raised to power minus 1, which gives us m naught Lt minus 2. So next we will see that intensity of gravitational field at a point due to a point mass. We are going to derive the relation of intensity of gravitational field at a point due to point mass. Consider a particle of mass m. Here is a particle whose mass is m. Let P be a point at a distance r from the particle. So this is point P, which is r distance away from the particle. To find the intensity of gravitational field E at point P. Now we are going to find intensity of gravitational field at this point. What is the strength of gravitational field at this point? Place a test mass m at that point. So we have to place a test mass m. What is test mass? Test mass means a very small mass, so that its gravitational field may not affect the gravitational field of bigger mass, right? So that's why we call it test mass. Then E is equal to F divided by m. Already we have read this formula. Intensity of gravitational field is F upon m, where F is the force exerted by m on small m. So already we have done F is equal to gmm upon r square. It is the force of attraction between any two masses. But also E is equal to F divided by m. So divide this whole equation by small m. This m and this m will cancel out and we are left with gm upon r square. Now E is directed towards the center of mass m. So this intensity makes this body to attract towards its center. Suppose that test mass is free to move, then it will move towards capital M with an acceleration of a. If this mass is free to move, it will move towards this object with an acceleration of a. Then if it is moving with acceleration a, obviously then force which is equal to m into a. This is the previous formula. When a body is in motion, then F is equal to m into a. F is equal to ma. Now here we are going to put F is equal to ma divided by m, and again this m and this m will be cancelled and we are left with a. Hence the acceleration of gravitational field at a point in gravitational field is equal to the free acceleration experienced by the test mass kept at that point. So we can say that intensity of gravitational field at a point is equal to the free acceleration experienced by a test mass at that point. Now, intensity of gravitation field on the surface of the earth. In the previous article, we have read that intensity of gravitational field at a point which is r distance away from the surface of the earth. Now we are considering that the mass is on the surface of earth, then what will be its acceleration due to, then what will be its intensity of gravitational field? Let's see. To find the intensity of gravitational field on the surface of earth, place a body of mass m on the surface of the earth. Now we are keeping this mass on the surface of earth. Force on this body is equal to Fgmm upon r square. Same formula where g is the gravitational constant. M is the mass of the earth and r is the radius of earth. Now we are not taking small r, we are taking here capital R because distance from center is equal to radius of the earth. So this distance is r, capital R. Now again formula of E on the surface of earth is equal to force divided by m. So we will divide gmm upon mr square. This m and this m will be cancelled and we are left with gm upon r square, and which is nothing but it is the relationship between small g and capital G, or you can say that acceleration due to gravity in terms of universal gravitational constant. Hence, the intensity of gravitational field at any point near the surface of earth is equal to the acceleration due to gravity at that point. Next is gravitational potential. Students, before going through this article, just recall that what you have read in your previous class about electric potential or potential difference. Here you can find some similarities between the definitions. Let's see. The first definition is the gravitational potential at a point is defined as the work done in bringing unit mass from infinity to that point. Now remember, in electric potential, the definition is the electric potential at a point is defined as the work done in bringing unit charge from infinity to that point. So in this case, we are not having charges, we have masses. So gravitational potential is similar thing. It is the work done in bringing unit mass from infinity to that point. Suppose this is the object which is at infinity, right? And we have written here 1 kilogram means to show that it's a unit mass, and we are taking this object from infinity to a certain point here. So amount of work done in bringing this object from infinity to this point is equivalent to the gravitational potential. So whenever you have to find potential energy, basically you have to find the work done, because when you got work done, that work done is stored in the object in the form of potential energy. Okay. the next definition is gravitational potential difference. So, gravitational potential difference between 2 points in a gravitational field is defined as the work done in moving unit mass from one point to other. Same definition, but here you have to replace from infinity to that point with from one point to another. So, this is the potential difference or gravitational potential difference, and this is gravitational potential. Now, gravitational potential is equal to work divided by mass. So, work SI unit is joule, mass SI unit is kilogram. Now, its dimension formula ml square t minus 2 for work divided by m for mass, which gives us m naught L square t minus 2. We get that SI unit of gravitational potential is joule per kilogram, and its dimensional formula is m naught L square t minus 2. Next, we are going to study about gravitational potential at a point due to point mass. Now we will have that relation, what is the value of gravitational potential at a point due to a point mass. So consider a point P at a distance r from the point mass m. This is point mass m, and this is point P where you want to find the gravitational potential. Gravitational potential at P is the work done in bringing unit mass from infinity to the point P. So let this point be at Q, which is at infinity, and we are taking that mass from Q to P, right? So amount of work done in bringing this mass from Q to P is called gravitational potential. Now Q, we are considering that Q is at infinity. Suppose unit mass is kept at Q at a distance x from the point mass m. So this is at a distance x from this mass. The force of attraction between the point mass m and unit mass kept at Q is F is equal to gm into 1 upon x square, where x is the distance between these two masses, capital M is the point mass, g is universal constant, and this is small m, which is equal to 1 because we are considering it unit mass. Now work done to move the unit mass through a small displacement dx is, I told you earlier that whenever you have to find the potential, basically you have to find the work done. Now this unit mass is experiencing a force F, and we are moving this unit mass from a small distance dx, and we know that work done is equal to force into displacement. Here dx is very small displacement, right? So we are going to put this value of F is equal to, from this relation, F is equal to gm upon x square multiplied by dx. So this is the small work done. So to find the total work done, we will sum it, and in physics we are going to use the calculus notation integral. So this is the second thing you should keep in mind. First thing, whenever you have to find the potential, you have to find the work done, and to find the work done you have to do integration of smaller work done. Here we are going to find the total work done, which is equal to integration of dw, which is the smaller work done. And one more thing, we are moving the object from infinity to a certain distance r. So we will write limit, upper limit r and lower limit infinity, f dx. Now value of f is gm upon x square into dx. G and m both are constants, so we are taking it out and now integrating 1 upon x square dx from infinity to r. The integration of 1 upon x square is minus 1 upon x, upper limit, here lower limit, because 1 upon x square is equal to minus 1 upon x. So this is the rule of integration. Now first of all we have to put the upper limit in x, then the lower limit. So gm bracket minus 1 upon, in place of x we are going to put r, it will become 1 upon r, minus and again minus 1 upon infinity. So minus and minus will become plus. but 1 upon infinity is 0. So this whole term will become 0. So we are left with W is equal to minus Gm upon R. Now this is the work done, and I told you that whatever the work done you are doing in bringing unit mass from infinity to that point, that is stored in the form of potential. So this total work done is the potential due to the point mass at m. So V is denoted for potential. So work is equal to minus Gm upon R. Therefore potential is also equal to minus Gm upon R. The potential at a point due to the point mass m is also equal to the potential energy of unit mass kept at P. So next article is gravitational potential energy. Students, there is a small difference between gravitational potential and gravitational potential energy. Let's see what is the difference. Gravitational potential energy of a particle at a point in a gravitational field due to a body is made by the work done. Again, it is equal to the work done in moving a particle from infinity to that point or infinity to the point. Now, what basically is the difference? In the previous gravitational potential, we have read that it is the amount of work done in bringing unit mass. But here it is the amount of work done in bringing the mass or bringing the body from infinity to that point. Here we are not going to consider unit mass. Here we are going to take its value, its mass will be considered. So mathematically it will be more clearer to you. It is equal to the product of potential, whatever the formula of potential at that point, and mass of the particle. Here we are not taking mass is equal to unit. Here whatever with the value of mass, we are going to take that one. So gravitational potential energy of m kept at P is equal to potential at P due to capital M multiplied by mass of that particle. So potential at P is equal to minus Gm upon R. Just we have done this article. Multiply it with the mass of that another particles. Then it will give you gravitational potential energy. So this is a slight difference between gravitational potential and gravitational potential energy. So now we are going to see gravitational potential energy of a body kept at a height h above the surface of the earth. Now let's calculate what is the value of gravitational potential energy of a body which is kept at a height h from the surface. The gravitational potential energy of a body of mass m kept at height h above the surface of the earth is given by U is equal to minus Gm into m upon r. This is the general formula, which is equal to minus Gmm divided by, now r is the total distance, r is the distance from this center to this mass, this is r, but actually it is equal to this r plus this height. So we can write r is equal to r plus h. Alright, now we have taken r common out of it, we will get 1 plus h upon r. We can also write this equation as minus Gm m upon r bracket 1 plus h upon r raised to power minus 1, which is the reciprocal of this denominator. M is the mass of earth and r is the radius, and small m is the mass of the body. Alright. Now if h is very small, if height of that object from the surface is very small as compared to the radius of earth, then 1 plus h upon r raised to power minus 1 is equal to 1 minus h upon r, which is according to the binomial theorem. So which gives us u is equal to minus Gmm upon r bracket 1 minus h upon r. Now open the bracket, it is equal to minus Gmm upon r plus Gmm h upon r square. Now if you remember, this Gm upon r square is equivalent to small g, which is acceleration due to gravity on the surface of Earth, and minus gm m upon r. This term, it is the potential energy of the mass on the surface of Earth, which is taken to be 0. On the surface of Earth, we will consider that gravitational potential energy is 0. So we are going to take this value, this whole value equal to 0. So what we are going to left with? In place of g m upon r square, we are going to put small g. So it gives us a value of mgh. And this is the relation which you have read in your junior classes, that potential energy is equal to mgh, mass multiplied by acceleration due to gravity into height. So this is how we can derive that relation. Solve some examples based on the articles just we have done. Calculate the gravitational intensity on the surface of Mars, assuming it to be a uniform sphere. Given mass of the Mars is 6.420 into 10 raised to power 23 kg. Its radius is equal to 3.375 into 10 raised to power 6 meter. So what are the given values? Mass of the Mars 6.420 into 10 raised to power 23 kg. Secondly, radius 3.375 into 10 raised to power 6 meter, and capital G, although it is not given but you have to learn it, universal constant, it is equal to 6.67 into 10 raised to power minus 11 Newton meter square per kilogram square. And we have to find E, means gravitational intensity. Now solution is equal to E is equal to gm divided by r square. Put the value of g, m and r. In place of g, 6.67 into 10 raised to power minus 11, multiply by m, which is mass of the Mars, and divided by r, which is radius of the Mars. After solving it, we are going to get 3.76 Newton per kilogram. Next example is, find the gravitational potential due to a body of mass 10 kg at a distance 20 meter from the body. Gravitational constant is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. Here given values are mass of the body 10 kg, radius is equal to 20 meter, and g value 6.67 into 10 raised to power minus 11 Newton meter square per kilogram square. Now we have to find potential V. Formula for potential is V is equal to minus gm divided by r. Again, by putting the value of g, m and r, we are going to get 6.67 into 10 raised to power minus 11 multiplied by 10 divided by 20, which is equivalent to minus 3.33 into 10 to the power minus 11 joule per kilogram. So this is the value of gravitational potential due to a body of mass 10 kilogram, which is at a distance of 20 meter from the body. Now you are able to answer all these questions. Question number 1. Define intensity of gravitational field. Give its SI unit. Question number 2. Show that the intensity due to gravitational field of the earth is given by the acceleration due to gravity both in magnitude and direction. Question number 3. Define gravitational potential and gravitational potential energy. Next question is, derive an expression for the gravitational potential energy of a body lying at a height above the surface of the earth. Next one is the numerical. Calculate the intensity of gravitational field due to a body of mass 20 kg at a distance of 50 cm from the body. And last one is, calculate the gravitational potential energy of a body of mass 100 kg at a distance of 6 km from the center of the earth. That's the end of the topic.